Hello, welcome to lecture 36 and the video 36 in my lecture Advanced Mathematic Modeling. So in the last, where do I have it? Yeah. In my last video I introduced you to the Levy flights and the main idea was that the sign of the increments was taken from the power law distribution and we got this random walks with these large jumps, which are rare but large. And so we said, let's have a look more closely at this power law distribution. And these power law distributions, they take a central role for describing many different processes. That's why we for the moment leave the area of random walks. Just have a look, zoom in on the properties of power law distributions to discuss them in more detail. And then we will come back to the random walks. Okay, let's write this down again. So what is a power law distribution? I mean, we have seen this now quite often, but let's write this again for completeness. So we have a random variable x, and the PDF of the variable is a normalization constant times x2 minus alpha. Okay, that's the distribution. And if you write it like this, at first it's a probability distribution like any other, like exponential, Gaussian, whatever, binomial, or I mean not be like a continuous probability distribution, but like any other. So what's so special about this distribution? So first let's plot the distribution. So if we take her, I had done this already in the last video, but this is so important we cannot repeat it often enough. We have here our p of x. So then we need our minimal value x0, our cutoff value. And then we have the distribution which decays with x. And if we plot this on a log-log scale, we should have done this a bit larger, so really see we have a very long tail of the distribution. And if we plot the distribution on a double logarithmic scale, then I have here log x, log p of x, and then we will find a straight line, and the slope will be minus, will be just, this slope will be minus alpha, because the slope is negative. And we take this negative sign out, so this alpha is a positive constant, but we mean the function is decaying. So okay, so what are the properties? So we calculated already a lot of properties, so I don't have to repeat this, just look up in the script. I just want to write down the main properties. So by normalization, we will find that this constant c is alpha minus 1 times x0 to alpha minus 1. This is something I can never remember. I have always to look it up or calculate myself, but that's just the normalization, which depends on our minimal value and it depends on our exponent. So now let's calculate the mean value. So what's the mean value of x? So I mean it's the didn't we calculate this? Let's write it down again for sake of completion. So like the x are always positive, so x is larger than 0, definitely. So in our integrals we only have to integrate from 0 to infinity x times p of x. and then we get, now we have to take this integral, plug in the normalization, and if we calculate this, maybe let's do it. So we have the normalization constant, we integrate from 0 to infinity, x to minus alpha plus 1. That's always the trick when we have to integrate over dx, of course. Here we also have to integrate over dx. So like when we calculate the mean, so the exponent is we get here in the exponent is plus 1, and so we now integrate this, so we get c over 2 minus alpha, and then we get here x to now minus alpha plus 2 in the borders from x to infinity. And now you see if alpha is smaller than 2, this would diverge. So only if alpha is larger than 2, I'll just integrate, of course, from here from x0 only, because only from this value we have contribution. Only if alpha is larger than 2, and then you plug in this normalization constant, then we will find this is alpha minus 1 over alpha minus 2 times x0. So the expectation value is then only defined if alpha is larger than 2. So if this distribution decays fast enough. So like, I mean, think like the slope, this exponent alpha gives us the slope, which tells us how important is the tail of the distribution. When we have large alpha, the tail is very small because the function decays fast. If alpha is small, then we have a very, very large tail. Yeah, and so you see, so if alpha is too small, then the mean value of the distribution is not defined. Actually, what I here didn't say you, I mean, when we calculate the same thing for the normalization, this only works if alpha is larger than 1. Yeah? So maybe let's write this down. So what is the importance of alpha? Importance of this critical exponent alpha. And this gives us the, so maybe first in words, small alpha leads to a long tail. And so if alpha is larger than 1, then we have this normalization. Or maybe let me write it different. If alpha would be smaller than 1, yeah, so very small alpha would be a very broad distribution, and then we have no normalization. Now, if alpha is larger than 1, but smaller than 2, then we don't have a mean. No mean, because then the expectation value of x would diverge. Yeah? So in this range the distribution doesn't have a mean. Now we can calculate this further. If we now calculate the second moment, and if alpha is smaller than 3, we don't need this. Alpha is smaller than 2, we don't have a mean. If alpha is smaller than 3, we don't have second moment. So no, because then the second moment would diverge if alpha is smaller than 3. And if alpha is larger than 3, then the second moment exists. So maybe let's make here a small graph. Maybe I make this graph here. So let's look at the range of alpha values that we can have of exponents. So we can have here 0. Alpha should be larger than 0. Then we have 1, 2, 3. So, and then if alpha is smaller than 1, we have no normalization. So basically we don't have PDF at all, because we cannot even normalize the whole thing. So alpha usually should be larger than 1. So now if alpha is larger than 1 but smaller than 2, yeah, then we have no mean value. This means we have a probability distribution, but we don't have a typical size of a random variable because the mean doesn't exist. If alpha is larger than 2, and between 2 and 3, so larger than 2, but smaller, if alpha is smaller than 3, we have no second moment, no standard deviation here. So this it's more mild. The larger alpha gets, the more mild the distribution will be. But still, we don't have a variation. But then at least we have a typical value of our random walk, of our random variable. But the standard deviation is still infinite. And only if alpha is larger than 3, we have defined mean and standard deviation. And let me write down these values. So we have the expectation value we have calculated here is alpha minus 1 over alpha minus 2 times x0, but only if alpha is larger than 2. And the second moment is, you can calculate it in a similar way as the integral before. This leads you alpha minus 1 over alpha minus 3 x0 squared if alpha is larger than 3. So this would be two formulae that appear very often. And so in this scale here you see how mild or how wild the distribution is there, because for small alphas you start to lose the standard deviation or the mean, or the distribution is not even normalizable anymore. And so this means, so typically then we say so that alpha should be in a range between 1 and 3. Because yeah, sometimes people look at even alpha is smaller than 1, but then you have to think what this even means, because like the probability distribution is not normalizable. So typically we say that's the range of alpha. So because why do we restrict alpha to be smaller than 3? Because if alpha is larger than 3, that's fine, it's a fine probability distribution, it has mean and standard deviation. But then if let's write it like here, if alpha is larger than 3, yeah, so there's nothing special anymore. So it's still a valid PDF, no problem. But since then the central limit holds, and if you from such a distribution then calculate mean square displacement, then you're in a diffusive range. So we can directly say, so like if we take our Levy flight, yeah, we take the increment, the step lengths from the power law distribution, but if this alpha is larger than 3, so then we have diffusion here, because then essentially the central limit holds. But if alpha is smaller than 3, then we enter the interesting range, because then if alpha is smaller than 3, we don't have the standard deviation, we don't have the second moment, the central limit theorem doesn't hold anymore, and we leave the diffusive class, and the corresponding random walk, this Levy flight, will then be super diffusive. Okay, so that's maybe first about here the different ranges, and then if alpha is smaller than 3, then we in this plot here we have these different ranges. So we have the many rare events, the many small events, the small x values. So typically, and this we discussed in the example of the Levy flight, so typically if we take such a value, it will be very small mostly, but here we have the long, or sometimes we say the fat tail. So rarely we can have an arbitrarily large number here. Maybe another information to make the slide maybe very condensed, but sometimes we're interested in the cumulative distribution. And this we calculated also at one point. So this p larger of x, and I just repeat it here again, is x over x0 to power 1 minus alpha. Yeah. So this means the cumulative distribution is again a power law, which has an exponent 1 minus alpha. So this is, if you make a log-log plot of the cumulative distribution, you have again a straight line, but with a slope which is plus 1. Yeah? So in order if you have data, you have a sample of random variables, and you think it might be power law distributed, so the first thing you can do, you plot the histogram on a double logarithmic scale and see if it's a straight line, and then your distribution might be a candidate for a power law. Or you look at the cumulative distribution, look if the cumulative distribution is a straight line, then it's also a candidate for a power law distribution. But beware, so there are many fake or wrong results in the literature, in the scientific literature, where people did this, saw some kind of straight line, maybe not over many orders of magnitude, and then they concluded, oh, my data is power law distributed, whereas then later it could be shown it was not a power law, because unfortunately if we don't have many orders of magnitude here, many distributions look a little bit like a straight line on a double logarithmic plot, and so this is a scaling regime with a straight line is not enough evidence to really see that we have a power law. At least you would need, one would say, maybe 2 orders of magnitude, then okay, you have more evidence that we have really a power law. But then if you really want to prove that your data is taken from a power law distribution, then you need some more sophisticated statistical tests, and maybe will come later to them. But so here I think I gave the most important formula that we need. So we have the normalization, we have the moments, we have the cumulative distribution functions, and I showed you the different regimes of alpha where this distribution has different properties. So with increasing alpha, the distribution gets more and more mild, and so we have this range between 1 and 3, and so that's the valid range. Maybe I should make this here in blue. So that's the interesting range here. And now, interestingly, many random walks that you find in nature have exactly an alpha which is here in the middle of this interesting range. So maybe it's time now to look at some examples. And so the interesting thing here is that this power law distributions appear in many, many different contexts. For example, famous are city sizes. So take a database of city sizes, so the number of inhabitants of cities in a country or a continent. You plot this, and then you will see that the distribution of city sizes follows the power law, meaning that you will have many small villages. So most, like, it depends of course how small the smallest value in your data bank is. So maybe you have a cutoff at maybe 1,000 people or 100 people, and say smaller villages you don't count anymore, and then here you go to the big like mega cities, like with 10 million people or something. And but if you take a random community or city, it will be typically small, but you have the chance to have such a big city like Tokyo or whatever, Mexico City or whatever. It's the biggest city in the moment in the world. Yeah. So very few very large cities, many cities are small. And so for city sizes, interestingly, so this alpha is about 2. Yeah? So and this fact that the power law, maybe we write it here, power law distribution with alpha about 2, it's very often called Zipf's distribution or Zipf's law. And so the power law distribution of city sizes is an example of Zipf's law. So Zipf was a scientist who was one of the first to find such power law distributions in empirical data. So take something else. Take the frequency of words in a text. So very often people, so you can take now, today we have many texts in all the social media, but when this analysis was done the first time, people just took a thick book. Maybe they, for example, they took Moby Dick. They take the book and then they make a list of all the words. Then they plot the frequency of words in the text, and then you have some words which appear very often, but most words appear only once or twice, so specialized terms. And then the frequency probability distribution follows the power law. Or you could have you could look at economics. And then you could look at the income distribution. Income. Or you could take the wealth distribution. So how many people earn much money, or how many people have a wealth of a certain money. Yeah? And then you will find that most people are poor, but then you have a few multi-billionaires like Albert, Bill Gates and so on, who have a lot of money. And again, this distribution follows a power law. You could look at sales curves. So like a bestseller list. So if you take books, for example, and then you see how many copies of a book are sold, and you have the bestsellers, so like the most sold books is still the Bible and the Mao Bible. Now recently also the Harry Potter books came in the top bestseller lists. So you have a few books which are sold quite often, and with high chance everybody will have such a book in his room somewhere. But then most books are sold very rarely. And again, sales curves, not only from books, but for other products also, sale curves typically follow power law distribution. You have this in power law distributions in biology, in ecology, ecology. For example, when you look how many the distribution, the number of species in genera, species, genera, then you have some genera which has many species, and most genera have a few species. You find again such a distribution. Take again something very different, go to geography, go to earthquakes. Here. And so what you measure with earthquakes, you measure the energy in an earthquake, so the strength of an earthquake. And if you make the distribution of the strength of earthquakes, it follows the power law. And this is here known as the Gutenberg-Richter law. And here the geologists on their own came to the idea to plot the distribution of earthquakes. So very often the earth is just vibrating a little bit, but sometimes you can have these big earthquakes which destroy whole cities. Yeah. And so the geologists, when they wanted to plot the histogram, came also to the idea that it's a good idea to plot the magnitude of the earthquake, so the energy released on a log scale. And this is called the Richter scala. So like if you give the strength of an earthquake, you take a log of the energy. Yeah, so earthquakes, you will find this in social networks. You will find power laws. Social networks. If you look at the number of email contacts, or email or whatever, Twitter contacts, Facebook, or the number of friends, and then you will find some people who are the influential people, who have a huge number of friends or followers, if you want. But most people just have a few followers, like me. So most people are normal, but then there you have the super duper guys who are connected to everybody. And in the social networks, you will find the power law distributions. So the list goes on and on and on here. For example, to show you something from my recent work, when the corona virus hit this year, so I looked for the number of cases, so the distribution of the number of COVID-19 cases in different countries. And when I was intrigued to look at this because when the corona started, we had it first in China and then in Italy. So you had some hotspots where hotspots of the epidemic. Whereas at this time, for example, I knew nobody who was positive with corona. So in most parts of the world, the number of infected people was still very small. And so then I plotted the number of confirmed corona cases for different countries, and I found this followed a power law distribution. So meaning, so you have a few countries where the disease is already very strong, whereas most countries the disease was still very harmless. Yeah, but this I did this analysis in the beginning of the pandemic. I'm not sure. I don't think this analysis holds for now. So once the disease had spread to many countries, this power law distribution doesn't necessarily hold anymore. Probably I'm going to tell you more about this here. In social networks, maybe to continue with the list. Let me just continue because it's so nice. You can also look at popularities of choices, popularities, for example, the frequencies of names, of first names. Yeah, so this goes like fashions. So some names are given very often to childs and others not so much. So the popularity of these names follows as a power law distribution. Of course, this changes because fashion is then always changing, and after some years the names which are fashionable change, but always you have their power law distribution. This popularities is very similar to the sales curve, the bestseller lists. I did also research there. We looked at popularity of chess openings. So where you see when you play a chess game, and then you can start with a certain opening, make some moves which are popular. And in chess, this was there's lists of this where you can look in the opening libraries, and we made an analysis, and we could show that there are some fashionable openings which are played most of the time, but you have also very rare openings. Again, the popularity of a chess opening follows a power law distribution. We can continue. For example, I was also involved in analysis of species invasions, in invasive species. Maybe you know this, that species now by transport, by shipping and commerce are transported in different countries, and we have this invasive species which enter habitats and have all kinds of effects. And then you can make a histogram. How many countries has a species invaded? And then you see there are some species which have invaded a lot of countries, like some ants or rabbits or the dove. But most species invaded only once, or one or two countries. So again, a power law distribution. So like our here popularity here, very often they studied their scientific citations. Maybe this is studied a bit by the bias of scientists, because like we scientists are always interested who reads our paper, who cites our paper, and then there is a few papers which are cited quite a lot, and many papers are not cited so often. So we find the power law in scientific citations. And in one of the exercises, I just for fun, in some of the last Olympics, I looked for the number of Olympic medals in countries. So so China or the US, also Germany had typically a lot of medals, gold medals or something, whereas many countries have only few medals. And this you will do in one of the exercises, and because I never found a publication about this, so you can do something which has never been published before, and there you also will see that the number of Olympic medals decay as a power law. And here as a side remark, if you're interested and you want to see how to write a scientific paper, if you did the homework and think that's nice, and you're interested in writing a scientific paper, just contact me, and then we can publish this and write a paper. Or maybe the whole group maybe wants to do this. This depends on your initiative. So, and that's now so if you look at these many examples, that's very striking, because like when you learn classical statistics, and I started in this course to show you the normal typical things. So we see we have the central limit theorem. Most random numbers are normally distributed, and very often it is like this. For example, if you have the body size of humans, and then typically they have a typical size of 1 meter, whatever. But you will never find a human of 5 meters or something like this. This simply doesn't exist. So very often you have just random numbers which come from these mild distributions, which are like exponential or Gaussian distribution. But there are so many other examples which are not of this class and better described by a power law distribution. And as we will see, the power law distributions have different properties. We saw already some moments are not defined. But so like if all the analysis typically goes by calculating the first and second moment and then looking for resulting properties, and this power laws this moments does not exist. So for all these familiar of systems from biology, economics, social systems, whatever, the normal statistical analysis does not hold. And that's maybe the kind of one of the motivations to make this lecture, because these are all processes which are so important. A lot of processes which go together with modern social networks, with globalization, with invasive species, with stock markets, with our modern economy, they all relate to this power law distributions. And also now we're entering an area where many data are available about social contacts, because like we can look just in the contacts in the social networks here, or in the scientific citations or chess openings. Suddenly we get data about popularities, and so in many of these new databases which in the last years are emerging in all kinds of systems, it's so easy, it has become so easy to plot and analyze these distributions. And frequently, and in many cases where I looked at this, I found power laws. Like in this chess, I found power laws. In the Olympic medals, I found power laws. In the where in the COVID, in this epidemics, I found power laws, and many other scientists also. So the thing is now, we want to analyze what's so special about this, and we learn something which is important for many processes of our modern life. Okay, that's so much about here either the basic properties of power laws, which I showed you here in this slide, and here a lot of examples. And what we want to do in the next videos is to look a bit more in the autonomy and the properties of these power laws. Okay, for the moment, thank you. And sorry, I just realized this video was getting a bit long, but there you see, that's my I get so enthusiastic when I speak about power laws that I couldn't stop myself. Okay.